Let me introduce our next speaker. That's Ilia Shumailov. And Ilia is going to talk about mounting attacks on enhanced neural networks, effectively increasing their energy consumption by a factor of 10 to 200.
Is Ilia. I am currently a PhD student at the University of Cambridge. I am approaching my final year. Recently, we've started exploring the field of machine learning and in particular adversarial machine learning, trying to understand how easy it is to manipulate things and how easy it is in practice to manipulate things. In order to understand ML better, I did an internship or like a visiting studentship at the University of Toronto, where I visited Nicholas Peppernot, who specializes in adversarial ML. And this work came out of this internship. So let me present to you sponge examples, the energy latency attacks on neural networks. Can we go to the next slide, please? Можно следующий слайд, пожалуйста. Great. So currently machine learning is everywhere. The world is basically buzzing with it. And the basic idea is, unlike classical computer systems, it's really hard to tell what's happening. And one of the reasons why that's the case is because it's all data-driven. There are no formal rules inside. Well, there are, but it's really hard to first extract them and second enforce them. One of the other things is there is a property which is inherent to modern ML, and that is the non-determinism. Namely, it's very often that machine learning systems operate over non-deterministic randomness pools. So often the network itself samples some randomness in order to make inference. And this randomness, so examples of this would be uncertainty quantifications. Examples of this would be noisy nets inside of RL agents or modern style GANs or something. And in such a world, it suddenly becomes super hard to define what security is. Even outside of safety, defining what a malicious actor is and what he can do and what he can't do is really hard. Furthermore, robustness becomes also very hard to define. What does it mean to be resilient and robust in the world of ML? Можно следующий слайд. So here I want to separate the two approaches. The first one is computer security in context of machine learning, and then machine learning in context of computer security. So when machine learning people talk about computer security, they usually talk about adversarial examples. And those are the small samples which are usually noticeable to the human eye, which end up thwarting the prediction of a particular model. So say you had a bird, and then you apply a small perturbation to it, and then suddenly it becomes a car. At the point of me giving this presentation, adversarial examples exist for practically all of the models, and there are no ways to properly stop them. As of right now, there is a very large taxonomy of different attackers. Namely, people have developed attacks that work in very different settings in very different environments. And those attacks and those attackers operate on a very different set of assumptions. So people usually separate white, gray, and black box settings. And white box talks about attacks which require information, like all of the local information about the model, practically everything about it. Gray box attacker allows you to emit some of the information, and then the black box attacker basically assumes nothing about the model. He only observes the decision that the model makes and then performs the attack on top of it. In computer security, not all attacks matter. As a matter of fact, we know way too many attacks, say, on EMV, but in practice, nobody observes this. And the reason for this is some attacks are just harder to pull off than the others. And some attacks are harder to pull off on scale. Like, it makes little sense to steal $2 of one person when you can steal $2 out of the whole worldwide world. So in this case, we call attack scalable when you can build one attack can actually use it everywhere. And in case of machine learning, attacks actually are scalable. There is a property called transferability, where it was shown that the attack samples that works against one model actually usually works against another model. And there's nothing surprising about it because, if you have one model which tries to distinguish cats and dogs, and you have another model which tries to distinguish cats and dogs. Ultimately, there are only so many cat features, and if you target them with your perturbation, then obviously you should be able to affect the decisions of both of the models. Can we go to the next slide, please? And then if we go towards the computer security side of things and think about machine learning, suddenly we realize that machine learning is actually just a small part of the larger pipeline. There are a lot of moving parts involved. There are a lot of computers on the way. There are a lot of small bits and pieces, bits and bobs, which are involved into making a single computation. And this covers from humans which are monitoring the systems operating to the actual hardware itself, which is involved into the computation. And from computer security lessons, we know that your system is as secure as your weakest component, so Achilles heel of sorts. When we deploy systems, we have super clear threat models, and there are very clear safety and security policies, and also safety and security cases where you prove that the policies you've outlined are actually what you're observing in practice. There is very clear existence of a trusted component base, so you always know exactly on what can actually break your security policy, and you always know what the underlying assumptions within the system are. And the other important thing is there is a very well-defined environment, namely you precisely know in what environment your system should operate correctly, and then if you take it to another environment, then it should stop working. And when we talk about ML, nobody actually mentions those things. It's very uncommon that people develop safety and security policies for ML systems and ML systems in the context of larger pipelines. Can we go next? And recently it became apparent that machine learning in the context of computer security is super, super important. So I just wanted to give 3 examples. A very recent one, this was from a couple of weeks ago. People on Reddit discovered that in one of the image samples inside of ImageNet, there is malware inside of it. It's nothing sophisticated. It's literally just directing you to a particular URL. But nevertheless, it's super funny that everybody is running their analysis on top of ImageNet. And actually, if you're using a bad image viewer, you may get in trouble. Another thing that came out of it recently was a bunch of CVEs on TensorFlow. Basically, you can often buffer overflow the thing, and basically occasionally you can do full code execution, remote code execution. So if somebody is loading models, that's problematic. Another thing which came out recently is that TensorFlow now outlines that all of the TensorFlow and checkpoints and the TensorFlow models are actually programs. So if you start adding additional instructions inside, actually TensorFlow will probably execute them. So if you're taking models from somebody else and deciding to run them on your machines, that might be super problematic because you can, in fact, introduce bugs and vulnerabilities and exploits, and people can exploit you. So if you're running something and the checkpoints are not coming from you, you should probably do it in a sandbox. So I hope I convinced you that the machine learning should be viewed through the context of computer security. So let's go next. So if any of you did a computer security course at the University of Cambridge, we have security courses from the first year to the final year. We always start the first set of supervisions with the same question. We try to define a set of common terms, so the common language we use in order to describe systems. So in here, this is literally from the first question. We have just a set of terms and we discuss them for an hour. with the students. And in here, I've highlighted with green. It's simple color coding where red means that the topic is not particularly explored in the ML space. And then green means that the topic is somewhat well understood. So, for example, privacy and integrity attacks in context of ML are somewhat well understood. So integrity would be all of those adversarial examples, and privacy, you see a lot of different systems coming out of trying to do private computations, and this is like MPC, homomorphic crypto, something like this. Whereas all of the other stuff is practically unexplored. And the basic idea here is that machine learning thus far has been basically observed through a very theoretical prism, whereas much more practical analysis is required in order to make sure that the systems which operate with ML and work with ML can be made secure. So in this particular talk, can you please press the next slide? In this particular talk, we will be looking at availability attacks. And this is one of the triad of the attacks and triad of security. So in here, I want to explicitly separate the two, the notion of safety and security. So security deals with malice. It is what happens with the system when malicious actor is involved. Whereas safety looks at the average case. So you may have failures, you may have accidents, but still, the idea with safety is that it's just an average case. Whereas with security, we're looking at the worst case. So what happens when the malicious actor comes into place, which decides to spend all of his efforts to manipulate your system? So as I'm going to be talking, I want you to start thinking about stuff in terms of the worst case scenario rather than the average case scenario, as we commonly do. Right, let's go. So availability. NIST defines availability as ensuring timely and reliable access to the user information with a stress on timely and reliable. Basically, we want to make sure that you're getting your information in time, and also we want to make sure that the data you're getting out of the system is the one that you actually requested, and it does not have that much noise to it. Okay. So in here, when we talk about availability, we talk about the existence of this so-called benign clean data, natural data, where as you give it to the computer system which is running ML, it returns you the result in a sensible amount of time. And then what we call sponge examples, very potent samples which end up consuming a lot of energy and cause increased latency in the response. Those are basically the availability attack samples we're talking about. So here it's important to separate the two concepts. There is a notion of energy, and then there is a notion of timeliness. So energy talks about the actual overall real energy required to perform computation, whereas latency talks about the amount of time it took to actually receive the response. The two are super intimately connected, in that modern hardware optimizes wattage per unit of time. So namely what they try to do is, and they try to keep this relationship somewhat constant. So usually there is a set of modes between which they are switching. And with this in mind, what happens is, usually you observe that your computation will consume more energy if it runs for longer. Also, there are additional artifacts. So if you are running at a very high clock and you're consuming a lot of energy, you're producing a lot of heat. As you're producing too much heat, your hardware starts melting. And in order to save your hardware from killing itself, you end up, well, your hardware usually ends up throttling itself. Namely, it reduces the voltage, it reduces the frequency at which it operates, and then this consumes less energy, this produces less heat, but your computations end up being slower. So in practice, the idea is as you reduce your clock frequency and you reduce your energy consumption, your machines should actually take basically the same amount of energy as they would do if your clock was much faster, but the overall amount of time it takes is increased. In practice, we actually observe quite the opposite with ML. Anyway, so we'll get down to it. Let's go next, please. So here we talk about the energy gap. So what is the energy gap? The energy gap when you're performing a single pass through the neural network. And note that here we're talking about a single sample. We only evaluate a single sample at a time. So normally, the most amount of energy will be consumed based on the number of operations. So, and this is usually fixed. So this is think about this as a number multiplied and that's max inside of your network as you are processing a particular sample. And then the second, the actual big energy consumption factor is the number of memory accesses. So you're required to store so much memory and as you're evaluating the network on this, and this because your memory is usually limited. This usually requires moving off the chip. So this is off the chip communication. There is usually some sort of a PCIe bus over which you're moving data back and forth as you're performing computations. So think about this as you had your data, you moved your data to your coprocessor, if it's a TPU or a GPU, and then you perform some computations and all the intermediate values, if there are too many of them, say activations or whatnot, you move to the disk, and then you only pull them backwards when you require them. And in general, there is a fixed number of memory accesses you actually need to make inside of a single forward pass in a neural network. And also number of arithmetic operations is fixed. So why is it that there exists an energy gap if everything is constant? Can we go next, please? So there are a number of reasons. In this particular paper, we talk about two of those. The very first one is the hardware optimization-based one, and the second one is complexity-based one. Indeed, there are numerous other optimizations which are used inside of modern hardware, which can be targeted with similar response examples. So in case of data sparsity, often there are computations involved in your neural network, which you don't really need to evaluate in order to receive the results. So usually the hardware optimizers exploit so-called data sparsity. So if there are, say, a lot of zeros inside of your matrix multiplies, you actually don't need to evaluate them because those things will always produce you zeros. Similar things happen with ones and minus ones. All you need to do is actually find that they exist, those numbers, and you can also build additional predictive measures in order to find when stuff will become zeros and you don't need to evaluate. Similarly, hardware often talks about tolerance in computation. So this is where you actually don't need to evaluate certain operations if the operands are too small or if the error on top of the operands is too large. And all of this stuff basically talks about exploiting data sparsity. So another use of data sparsity is, remember how I talked about data moving off the chip and through some data bus. So the other thing you can do with sparse representations is that you can very efficiently encode it. So and here I'm talking about stuff like run length encoding or something, where basically instead of sending 10 zeros, you can send two numbers, 10 and 0. So 10 more zeros are about to come. And then the overall traffic on top of your bus is generally decreased. So can we go next, please? So the other thing which can be exploited, the other optimization that can be exploited is the computational dimension. So remember how I said that everything is constant inside of neural networks? Well, this is not actually technically true. And the reason for this is the overall complexity and the computation dimension, which is added on top of the network itself. So usually networks are actually a part of some loop. And an example of this would be all of the autoregressive models. And usually we are either talking about time sequences or sequence-to-sequence predictions, or NLP are a good example of this, of the autoregressiveness. So autoregressiveness talks about the fact that all of your subsequent computations actually depend on your previous computations. So in NLP case, for example, we're talking about you produce a single token, say we're talking about translation, you produce a single token, and then you use the same token as input for the next subsequent run. And because this stuff happens in the loop, suddenly an attacker can actually target those loops. And as they are targeting those loops, they can basically make sure that the that the network, as it's evaluating a piece of text, ends up doing this for very long. So for example, if you have a very long translation, because this loop will be producing token at a time, if the overall number of tokens it needs to process is very large, then it has to evaluate the network over and over again. And this is obviously going to be consuming energy. The other thing that actually happens with modern neural networks is that when dealing with very, very complex tasks, often you can't actually represent the task too efficiently. So an example of this would be actually performing, again, let's talk about NLP in this case, actually representing a very rich dictionary. So when we talk about language, there are basically numerous, infinite number of ways in which you can represent the language. I don't think the number of words is finite in our case, and obviously there are local slang, so you will always be able to add additional tokens inside. However, you can't really make your dictionary infinite because the complexity inside of the model, it just gets way too crazy, and also training those things becomes impossible because they are too large. So what happens in practice is that people take the inputs and then they compress them in some way. So it's very common. It's the state-of-the-art approach right now is to use BPE. This is the byte pair encoding. It is like byte pair encoding we know from information theory, but not really. The overall idea is the same. So if you take a word in any language, you'll discover that usually larger words basically consist of other words. So in case of Russian, for example, we're talking about prefixes, suffixes, postfixes. And all of this stuff can actually be processed separately. So, and if you take a single word and you break it into a number of subwords, you can, in practice, represent it much more efficiently. So, because suddenly you don't need a token for the whole word, but you can have a token for the subword. And this helps to cut down on the dictionary size and basically speed up both the computation, the training, and also improve the richness of your dictionary. The other thing it allows you to do is that it allows you to actually deal with the out-of-dictionary word. So, for example, if you don't know the word cat, dog, katapes, you know cat and you know dog, so you can actually represent them. And then even if you don't know the word, you can basically tell its meaning. And NLP tools exploit this in order to get good accuracy. So can we please go on? So just a very, very brief explanation of what I've mentioned above. So on the left, you see the autoregressiveness. This is a very rough sketch of what actually happens with the translation transformer models in the NLP pipelines. Basically, you tokenize stuff. Once you've tokenized, you encode this, and then you have this while loop on line 7, which basically goes until you see the end of sentence. So in practice, this can actually run forever if it never produces the end of sentence thing or somebody kills it. And once you've done this, again, encoding, inference, you then decode the token, you add a token, and then this goes on basically at line 14, you go back to line 7, and you keep on evaluating this. And because on line 11, you end up doing the inference, this inference consumes a lot of energy. So if an attacker can control line 7, suddenly line 11 will be consuming more and more and more energy. And you don't necessarily increase the input size here. Note that the input itself can actually be fixed. It is just what actually happens with the output on line 7. Right? So, and to the right, we talk about variable IO representation. So here we're talking about asazagoraphobia. This is basically the fear of being forgotten. If you just take this and you take a very commonly used English dictionary for representation and break it down into tokens. So you start encoding this. You encode it with 4 tokens based on how frequently those subwords are commonly used in modern ML. If, when typing this, you make a single error, and we are talking about not the O turned into a P, suddenly the representation of text changes from 4 tokens to 7 tokens. And if you think about this, this should in practice increase your energy computation by almost a factor of 2 already, because you're operating, if you're doing token by token processing, of course, because suddenly you are operating not just on 4 tokens, but 7 of them. And this is all just impact of a single error. And note that here we are talking about inputs of size 16, nothing too large, right? So, and then you can take this example to the extreme and say, can an attacker actually build an example in which it's not 4 tokens or 7, but the actual worst case scenario? Here, suddenly you can turn the 16 character input into 16 tokens. And this should, in practice, take at least 4 times more in terms of latency than the original word. Note that tokens are actually used both for inputs and outputs. So you read in tokens and you output tokens. So the variable IO representation matters for both inputs and outputs. And in practice, that means that if an attacker can control your representation in terms of tokens in the input and output space, he can actually, he or she can actually cause big disruption. Can we go next, please? So why does this matter? I just wanted to give a very quick example of a system in which attacks like the ones I described in this paper matter. So, I mean, I was told that there is a simultaneous translation in here. I guess this is one of the examples of the system in which you can exploit with the attacks we've described here. Namely, you can make sure that the text does not correspond to what is being said, or it just takes too long to process it. In case of the real world, I think the biggest killer application of this is cognitive radar. So cognitive radar, for those who are not familiar, is like an adaptive radar, but a lot more flexible. So adaptive radar usually operates on a set of modes, which the operator switches between depending on what sort of error you can deal with. So either range error or velocity error. And in case of cognitive radar, this is basically learned. You have a machine learning system which does the tracking and decisions on what mode, in which mode your pulse Doppler radar is supposed to be operating. So, but the underlying assumption is you are working with very, very precise times. You have to make sure that the latency is always constant, so a real-time system. And if you are capable of actually disrupting the real-time assumption of the system, namely increasing the amount of time it takes for the latency, suddenly you can introduce a lot of artifacts into the radar. Namely, you can hide targets, and also you can introduce targets. And this should disrupt the operation of cognitive radar quite significantly. So, and I put a picture of the dolphin over it is because dolphins use cognitive radar, bats use cognitive radar, and there are other examples of animals. Very, very nice technology. Right, so let's go on. So in the paper, we talk about multiple ways to build the sponge examples. However, the main way, the most important and interesting one is the Blackbox genetic algorithm way. So, and the basic idea is super simple. This is just from evolutionary algorithm family. You take a genetic algorithm, you have your system, you send a sample to it, you measure how much time it takes to respond, and you basically add it to the pool. And then you keep on evaluating more and more samples and storing them in the pool. Once you've stored them in the pool, you pick out the best performing samples, you morph them together, and then you try this again and again and again. And as you're doing this, over time, the amount of energy that is consumed on a single sample will increase, and you basically converge to a pool of samples which are super potent. We found that the very generic approach of differential evolution does not really work. It works in some examples, but it doesn't work too well. We found that the actual domain-specific optimizations work a lot better. So in case of NLP, we actually split words into left-right. Then we combine left-right, left. We basically take child one, we take the left part of it, we take child two, we take the right part of it, we concat them, and then we apply the random mutation on top of it. In the case of computer vision, we take two samples, we combine them randomly with a random factor, and this is more like differential evolution, and then produce another sample. And this ended up working a lot better. Can we go next, please? Interestingly, we've also noticed that you can perform a much more targeted attack for the sparsity objective, where if you actually just increase the activation norms across all hidden layers, that ends up working super well on a range of networks, so well that you actually hit the maximum possible theoretical representation, non-sparse representation within networks. If you ask me why that happens, I think Relo is to blame, but I'm not sure why. I just tried it once and it works super well. And then in case of the genetic algorithm, you can actually run it in a white, gray, and black box settings. So namely, you can, in the interactive mode, namely, you can either optimize on top of the latency measurements or energy measurements directly, or you can assume that you have the actual access to the model in the white box, and then you can sample weights and actually perform measurements on the individual computations involved inside. Or in the black box manner, you can just literally just time the amount of time it takes for a single sample. And all of those things work. The other thing we evaluated was the idea of a blind black box, where you're actually not allowed to interact with the model which you want to attack and exploit, but rather you can basically build a sample on another model to which you have access, and then transfer the attack sample to the model which you want to attack. Okay, let's go on. Can we go to the next slide, please? Yep. So as we evaluated the stuff, so there are multiple things to note here. We evaluated in the actual paper on a lot more benchmarks. This is just a cut down. And we basically run stuff in case of NLP on superglue and on a set of translation tasks. Please note that the input size, as is shown on the left, is fixed. Nothing is changing with it. Like the input, the number of characters in your input is fixed. We are not increasing the input size, but rather we're increasing the contents of this input. So the increase will come in the token representation, and the increase will come in the internal computations, and the token representation is both in the input and the output space. The other thing to mention here is that all of the input sizes are very small here. Like actually super small here. In practice, you will discover that modern ML as a service allows you to go as high as 10,000 characters, or even some allow you even more. And the attacks we show here will be a lot more potent if you increase the input size, because obviously the scaling increases significantly. The other thing to mention here is that we run the attack with a very limited set of parameters. And the reason for this was, obviously, first, we have limited computational resources at our hands, and second, you don't really want to burn too much energy. Our planet is hot enough at this point. And then I guess the final thing is that it didn't strike us that as you're running your availability attack generation, every subsequent run in your generation will take slightly longer because you need to process every single sample. So, and suddenly you're in a world in which it used to take you, with a single sample, an hour to run the proper evaluation, and now it takes a month to perform this single evaluation, and this obviously limits the extent to which we can evaluate the stuff and extent to which we can operate with input size. And obviously there are additional problems, like you basically hit, we hit a limit in which we can't go into any larger input sizes because our hardware does not have enough memory to actually fit all of the memory that all of those models end up producing and requiring. So long story short, if you try this on your very nice fancy hardware, your energy consumption is going to be a lot higher than ours, and also your time consumption is going to be a lot higher than ours, and this is expected. So those numbers basically are very rough, and think about them as lower bound on computation, because I can run them in a couple of months. So long story short, we show that we can generate samples, and those samples take, in case of this evaluation, it was up to 150 times amount of the energy and up to 70 times amount of time. In practice, in the actual paper, we show slightly higher numbers. Note that your mileage may vary depending on what hardware and the amount of memory you have. But in practice, this shows that on all of the benchmarks we considered, we ended up causing massive disruption, both in terms of energy and time. And those are very, very significant numbers. It's really surprising how easy it is to actually disrupt NLP models and with the availability and basically latency and energy attackers. The interesting thing here is we discovered that some languages are a lot easier to manipulate than the other, and I think it basically depends on how wordy the language is. So I think Russian is one of the wordy ones. So Russian models are quite easy to exploit. So can we go next, please? Can we go to the next slide, please? Right, so going into the computer vision space, here we are talking about sparsity attackers, because in computer vision there is, as of right now, there is no computational dimension, so we operate on fixed input sizes, and there are no loops around it. And we target the actual representation within, so the number of basically computations which can optimize the way. And we find that for some of the networks, we can basically, like a dense net one-to-one, we can basically completely remove the optimization objective, the optimization that is brought by the emerging hardware. And in case of other models, we basically end up causing disruption, which ranges between basically 8% to 20%, which is quite significant from the sound of it, but in practice, actually, it's quite small. If you try measuring it, you actually need to use statistics in order to measure the impact, because the actual amount of operations involved is not too high. So although you cause a disruption to the cost associated, and you cause a disruption to the latency associated, the impact is not too large. So for example, in case of mobile net, this is a common benchmark for embedded devices. You'll find, so mobile net is basically half a billion operations. Sorry, 500,000 operations, what am I saying? And there we end up increasing it by basically 8%. And if you try to measure this, you basically need about 300 samples to statistically, in the U-test, say that, yes, you ended up consuming more energy and more time. But on all of these details, please refer to the paper. We described this quite a bit there. Can we please go next? So here, let's have a look at what actually happens with the black box attacks performance. So we took an English to French translator on VMT16 task. So the way to read this is on the energy and time attackers, A and B, are both black box. So they don't assume anything about the model. All they do is measure the time or energy of the computation. And C is the white box attacker. So the ASIC is the actual attacker which runs with the knowledge of the model itself. It basically performs much more fine-grained measurement of the computations involved. And I show what happens to the energy time and ASIC cost as you perform the attack. So basically, although the time attacker itself is a black box, when I show the ASIC, I show the ASIC cost at a particular point of time of the attack, right? So, and as you can see, basically both energy and time are very noisy signals. They are not as nice and smooth as the ASIC measurements, but they basically follow very closely to what happens with the ASIC measurements. In fact, they follow it very, very, very close for NLP tasks. And this basically shows that if you want to perform attacks on NLP, availability attacks, and discover those sponge examples on NLP, your black box attacks, interactive black box attacks, are basically as good as your white box attacks. And all you need to do is just measure the time, which you can always do, well, depending obviously on how nice your network is, or you can use energy. So if you have a way to sample the energy of the hardware platform with which you interact, if you are sitting on a socket, you can measure the amount of current that flows by or something. You can always do this. So long story short, interactive black box works very well, both with the energy and time attackers. Can we go next, please? So here you may want to ask a question of, do sponges exist in practice? So namely, can we actually perform an attack on an actual system, not something in our home and over the network, obviously? So we took, we're currently in the process of responsible disclosure. We took one of the systems, one of the systems provided by a big provider. Again, we took just the translator, and we run the black box attack, namely the time measurement attack. And what we've discovered is we again picked somewhat of a small size, slightly larger than what we did on our platform, but not too large, and we ran the attack. And what we discovered is that we could consistently cause super large disruption to services. So we are talking about the performance degradation of factors of thousands, not hundreds, as is shown in our paper. And all this with, again, very relatively small samples. And the overall, basically, the overall lesson here is that you can perform the interactive sponge construction over the network. And there are no problems in doing this. And modern ML allows you to do this. So say you have a GPT-3 access and you want to run your attacks, you can actually do this. They limit the number of queries, but that's exactly perfect because they don't actually limit the amount of computation. And the same query, the same input size query, can cause a lot larger performance degradation. Can we go next, please? Right, so what are the lessons from the sponge examples and what do we do with them? So the main lesson from the computer security here is that optimizations almost always increase the attack surface. So, and usually when we talk about optimization, we talk about either side channel attacks or denial of service attacks. In case of the paper we've seen here, we see both. We see both the side channel attacks and denial of service attacks. Side channeling things, we've discovered that on a number of occasions we can actually turn off the drivers and turn off the hardware because we overheat way too much. Basically, the temperature resolution is not large enough. And what happens is we manage to push with a single computation of an NLP network, we managed to, even if you have a throttling temperature of 84 degrees, we've managed to increase it to 100 and then it just turns off. But no, 90 something, and then it just turns off. And in case of denial of service attacks, obviously, if someone is running sponge examples on your system and you try to do some computation at the side, you're going to struggle because this stuff just has the utilization of almost 100% all the time, and it just keeps on consuming and doesn't see an end to it. So we've shown that the optimizations widen the average to worst case performance for the time energy gap, and obviously this is the gap that can be exploited. Another thing to mention here is that in classical computer security, when we talk about side channel attacks, we don't really know what to do with them properly. So a recent example would be SpecTrack, which is built on top of speculative execution. So those are also latency-based attacks. And as of right now, it's not fully fixed. The new variants are coming out all the time, and basically, from what I understand, the main trade-off here is you either remove the optimization altogether, and then you have security, or you keep with the optimization and the security is gone. Who knows? Who knows what's going to happen? So in the paper, we talk about a very simple defense. Namely, we said, so what happens if you just measure the time and energy, and then if something is taking too much, then you just stop it. Obviously, this works with this thresholding approach, but in practice, this will introduce way too many false positives, and also it will make jamming very easily. We've shown as in the example in one of the slides that even if you make a single mistake in a sentence, you will cause an increase in performance by basically almost a factor of 2. And obviously, this is how to model this properly is an open question. It's as of right now, it's not clear to us how to actually build defenses against those kind of things. So another thing to mention here is that obviously sponges have to be modeled for real-time systems. You need to make sure that the computations happen, and as we have with other things, in case of regulations on autonomous vehicles, we probably want some fallback systems which are a lot less vulnerable to sponges. But it's also an open question. Who knows what one can do with this stuff? Can we go to the next slide, please? Right. So in this paper, to conclude, we've shown that it's possible to attack both model availability. To attack model availability in both white box and black box settings. We have shown that you can build attacks which target hardware optimizations. So this is the sparsity optimizations for CV tasks. And in some cases, they can completely turn off hardware optimizations. We have shown that attacks can target algorithmic complexity. And this is where we can target, for example, NLP tasks, which are complex inside of them. And you can cause big degradations, even for very small benchmarks. And then for bigger benchmarks, obviously, your impact will be a lot larger. Another thing we've shown is that the average case is very different from the worst case scenario. And the implications of this is that when people talk about the impact of ML on climate change, they may have been actually underestimating the impact there. So usually we say that half of the, a carbon produced by half of the lifetime of a car equals to the carbon produced by training a single transformer model. But obviously, if tomorrow this transformer model is actually used to operate on very badly formed data and ends up consuming actually a lot more energy consumption than what it was consuming in case of very nice and clean data, obviously the impact is much larger. It is not clear how to defend against sponge examples. But what is clear is that one should start thinking about availability of your ML systems and actually model the availability attacker, especially for the real-time systems. Can we go next, please? So thank you very much for listening. If you have any questions or you want to read further, there is a link on the slide. Please don't hesitate to reach out to me. I am responsive, and I would love to hear what you think, especially if you know how to protect against this stuff. It's really annoying to think about all the things one can do with this, because it's clearly damaging to all of us. Thank you very much for your time.
Спасибо, Илья. Спасибо, это очень...
Thank you very much, Ilia. This has been a very interesting report. The question I have personally is as follows. So a physical representation of these sponges, I understand that a sponge must be more than a query, right? A query to database. So what's the physical interpretation of these sponges, so to speak?
На самом деле,
The short answer is yes. If we're dealing with NLP models.
Doesn't matter.
Doesn't matter. Okay, I'll respond in English in case there are some English listeners. So the question was, is there an actual physical representation and interpretation to the sponge examples? So in case of NLP models, so from our experience, this is usually the attacks usually target the token representation of the models. So namely, they end up having representations which are very badly represented token-wise for the particular language. Interestingly, because modern models operate over the whole UTF-8 space, usually those are just targeting Chinese characters or Japanese characters. They end up representation. Obviously, this is also operating on top of the byte space, so you can they end up being very interestingly represented. Oops, sorry. The other thing to mention here is that the attacker, sorry, disruptions in the background. The token representations, despite being super fluffy, they end up being and super dense. They end up producing very high confidence values for the models. So similar artifact that you observe for the out of distribution example detection, you're observing here, where your samples, your model is very confident in what it's producing. Sorry, somebody is really. Let me open the door 1 second. Apologies for that.
Окей, спасибо тебе, Илья, за интересный.
Thank you very much, Ilya. This has been a very interesting report. I hope it will provide a lot of food for thought, not just for the attackers, but also for the defenders. And we'll be looking forward to other breakthrough ideas and reports from you. Thank you very much. Have a great day.